Welcome students. Welcome to the video on the operating principles of JFET. So in the previous video, we have discussed about the construction of JFET. We know that the JFET consists of three terminals, that is one is gate and then drain source. So the channel is the formed by the substrate. On both sides of the channel we will be having the gate terminal. So the width of the channel is controlled by the applied gate voltage. Here, coming to the diagram on the VI characteristics of JFET, we know that this is the construction of the JFET. So here, these two are connected, these two P region are connected together and it is the gate terminal. And here in the center region is the channel. The current will be flowing always from the source to the drain. So based on the applied voltage, we can study the properties and also we can study the operating operation of the JFET. So assume that initially I give here VGS is equal to 0. So VGS is equal to 0 in the sense that I make my gate voltage is equal to 0. So when my gate voltage is equal to 0, so there will be two PN junctions at the two ends, and because of that there will be an uniform channel width. The channel width is given here in this is the width of the channel, that is the gap between these two p region is nothing but the width of the channel, and hence because of this there will be a current flow. So the current flow will be linear and JFET will be acting as an resistive region. Now if I increase my gate voltage, that is if I try to increase or reverse bias my gate voltage, since it is an n-type material, n-type channel, n channel, so the P is nothing but my gate terminal. To reverse bias it, I will be giving a negative voltage. So VGS is equal to minus V1. So when I apply a reverse bias, we know that the junction will be getting reverse biased here, and hence of that due to the applied negative voltage there will be depletion region, or the depletion region will be increasing. So the increase in the depletion region will reduce the size or the gap here and hence the channel width. So because of that again the path will be same, that is the path will be from the source to the drain, and there will be a uniform current, but here what happens is the channel width increase, hence the resistance of the device will be getting increased. And so the graph we can see that again the current ID versus VDS is a linear current, will it's a linear process but with reduced amplitude. Still when I increase my negative mm, voltage, that is if I try to give VGS is equal to minus V2, that is V2 is less than V1, when I try to give this voltage, so it get more reverse biased, and because of that the channel, the depletion region increases, and because of this the channel width gets reduced further, and at one point both the depletion region may touch together, and that point is called as the pinch off point. So and when VGS is equal to minus V2, we can see that the channel is almost closed, and hence the current through the device will be equal to 0. So when VGS is equal to minus V2, this the dotted line along the x-axis gives that the output current will be equal to 0. So we can say that the VGS or the applied voltage at the gate terminal VG, it controls the channel width. So the channel width decides what is the current flowing through the device. So we can say that the VG or the voltage which is applied at the gate terminal will control the current flowing through the device, the output current, and hence the ID. So this is called as an voltage control device. So in the next graph, we will be seeing what happens when I change my VDS. So assume that I keep my VGS as constant, either VGS is equal to 0, assume that I am having VGS is equal to 0. Now what happens is I try to increase my voltage applied to the drain terminal. Initially, we assume that VDS is a very small value. So because of that, the channel here will be uniform throughout the device, and hence there will be a current flow, and the device will be in the linear region, or it will be in the resistive region. And as I increase my applied current, that is when applied voltage across the drain to source, that is when VDS is more positive, so there will be more current flowing through the device, and because of this current there will be a voltage drop across the along the channel, and this voltage drop will reverse bias my PN junction, and because of it what happens is the depletion region also increases. But the change in the depletion region is not uniform throughout the device, and we can see that the depletion region will be more towards the drain when compared to the source, or the depletion region increases as we go from the source to the drain terminal. And still when I so now the channel will be having again the same resistance with low current flowing through it. Now, when I go for more voltage at VDS, that is when VDS is applied more positive voltage, so the channel decreases, and on one point, both the depletion region may touch together, and hence there will be an constant current flowing through the device, and the device is said to be in the saturation mode. So that particular point at which the current goes to constant is called as a pinch off. So after pinch off, so here now the current will not be function of my applied voltage, and now the current will be function of the applied gate voltage. That is now it acts as a constant current source. So if I increase my voltage, my output will be changing. So now it acts as a current source. My device acts as a current source. So here, this gives me the family of the characteristics curve of an JFET. So initially, I assume that VGS is equal to 0, and then I draw the curve. So here I can see that there will be a linear region, and then resistive region, and then the saturation region. Similarly, the value of VGS that makes ID approximately 0 is called as the cutoff voltage. So this is called as the point at which my current is almost 0 is called as my cutoff voltage, and similarly the value at which my current starts to be constant is called as pinch off voltage. So the pinch off voltage is equal to 5 volts, or it can be minus 1 volt when not when VGS is equal to minus 1, there will be a pinch off at lower values. So here when VGS is very large negative value, ID will be equal to 0. That is when VGS is equal to VGS off, my ID will be equal to 0. And when VGS is equal to 0, the current through the device, I will be calling it as IDSS. The JFET will should be operated between the 2 points, that is when VGS is equal to 0 and VGS is equal to VGS off. The pinch off voltage and cutoff voltage are both the same value, but they will be in opposite sign. So now here, again coming to the drain characteristics curve, the drain characteristics curve is nothing but the curve which is drawn between the VDS and ID. So the y-axis is nothing but my ID. The range will be from 0 to IDSS, and the x-axis will be VDS. That is, the range of this will be from 0 to infinity. So the A to B region is called as a ohmic region, where ID increases proportionally with increase of VD and VDD, and VDD increases, VDS increases as VDD increases. It's called as a ohmic region, and VDS and ID are related by Ohm's law. The B is a pinch off point, the curve level of, that is from where the ID remains constant. So from B to C, it is called as a constant current region or the saturation region, because as VDS increases, the reverse bias gate to drain voltage VGD produces a depletion region large enough to offset the increase in VDS. The current is called the maximum drain current. And the next region is the breakdown. This is where occurs when ID begins to increase rapidly with any increase in VDS. This can cause irreversible damage to the device. So JFET is always operated well below this value. So in this video, we have discussed about the VI characteristics of JFET, and we have seen how the output current changes when I change my VGS and the VDS, that is through this supply voltage. So in the next video, we will be discussing about the other characteristics. Thank you.